Swayam Prabha. Digital India. Educated India.
Welcome back, and let me remind you that last time we were discussing the reciprocating tube hopper feeder after we have discussed the vibratory bowl feeder. Now, the reciprocating tube hopper feeder, this is also a feeder which is used for small engineering parts, and here the design I will remind you that through the mass of the part which is located in the bowl. Okay. Now, the tube reciprocates and the tube has a hollow inside, and the hollow silhouette of the tube is accordingly, as I said, accordingly made as per the part shape. When the tube reciprocates, so through the hollow part of the tube the parts can come to the outlet. So, here in this design, as I said, that there are certain aspects which have to be considered, and one of the basic aspects is that the part should not jam between the side of the reciprocating tube and the hopper wall. So, for that let us I have already discussed it, that if we have the part jamming like this, we have the three equations that we can find out. These are the force, this is the force balance equation along the vertical direction. Okay. This is along the horizontal direction, and this equation we have drawn by taking the moments about the point A. Okay. So, from these three equations, the value of W we can take from this first equation and put it in the third equation, which is coming here. So, W from the first equation is this. So, we are putting it in the W here in the third equation. So, we are getting this expression, and since F2 is equal to N2 into mu s, so we are getting this, and then we are rearranging because the N2 is actually this value. All right. This you can find out from here, like this we can write as the N2 and the cos phi plus F2 divided by N2 and the sin phi. Okay. So, we are getting the N2 common. So, F2 by N2, and F2 by N2, this is nothing but the mu s. Okay. If you see that F2 is the friction force, so therefore, F2 by N2, this is the mu s in the sense that coefficient of friction between the hopper wall and the part. So, this will be cos phi plus mu s and the sin phi. So, therefore, from this equation N2 is equal to N1 divided by cos phi plus mu s and the sin phi. Okay. So, this expression we are using here, okay, instead of N2, and we are getting the value as this. So, finally, what we are getting is that F1 by N1, this has to be equal to mu s, static coefficient of friction, divided by cos phi plus mu s sin phi. Okay. So, this condition has to be satisfied, so that the part is at the verge of the jamming, because this is equal to, we are saying. Now, the maximum value of F2 is given by the mu s and the N2, we have seen that, where mu s is the coefficient of static friction, and thus writing F2 is equal to mu s and the N2 in equation 4.2, 4.2 is here. Okay, this is 4.2 equation, this is, as we said, 4.1, and this is, let us say, 4.3. So, putting it here in the 4.1, what we are getting is in the 4.2 and equation 4.4, and eliminating the N2, we are getting F1 by N1 is equal to mu s divided by cos phi plus mu s sin phi. Now, for the tube to slide, what happens that F1 by N1, okay, F1 by N1, this has to be more than the coefficient of friction, all right, mu s. Therefore, from equation this 4.5 for from this equation we can say from the tube to slide, that so that the tube is able to slide we have to have that f1 by this or 1 by cos phi plus mu s sin phi have to be more than 1. Okay. So, this is the condition that has to be satisfied. In that case we have two parameters. One parameter is that angle, that is the most important parameter, and the another angle is the coefficient of friction, and the mu s will depend actually on the material of the part and the material that you are using for the hopper wall. Okay. So, let us say this is fixed because we have selected that. So, therefore, most important part here is this angle, which will actually decide whether the part will be jammed between the hopper wall and the side of the reciprocating tube, or other way saying that whether the tube is able to slide. If the phi is not properly selected, in that case the tube will not be able to slide because the part is jamming here. That is the idea, that is the point that we are telling. Okay, so, this is the condition that we have to always see, that 1 by cos phi plus mu s sin phi have to be more than 1. The expression indicates that the value of phi should be as large as possible. You can see this from here. Okay. To prevent jamming when mu s is large. Okay. However, when mu s is less than cot phi, the parts cannot slide down the hopper wall. What we are taking is that this is some absurd value, we are saying that if mu s is less than cot phi, which is cos phi plus divided by sin phi, it is an absurd. So, this is stuck, I mean the parts cannot slide down the hopper wall at all. So, we are taking that as a condition, and therefore, we are saying that the best compromise is probably given by writing the following two limiting conditions. So, we are saying that since it will not be able to slide, so if mu s is equal to cot phi, and then here we are saying cos phi plus mu s sin phi is equal to 1, this will be the limiting condition. Okay. So, from this limiting condition, combining equation 4.7 and 4.8, this gives, if you solve it, you will find that phi is equal to 60 degree. Okay. Now, on substitution of this value in expression 4.6, if you go here, all right, this it is found that to prevent jamming under these conditions, that is when we have these conditions, the coefficient of friction mu s must be less than 0.577, meaning that if we have phi is equal to 60 degree, put the phi is equal to 60 degree here, and you will find out that the mu s, this is equal to something around somewhere around 0.577. So, this will be less than 0.577. Okay, if this condition has to be satisfied, that this is more than 1. So, in that case what is happening, this value is greater than expected in practice, in the sense that normally in practice the material that you use for the hopper wall and the metal parts that we are using in the inside the hopper, normally for that combination of material this value is greater than expected in the practice. So, therefore, it may be concluded that with a hopper angle of 45 degree instead of 60 degree, for which we are getting mu is equal to 0.577, with the iteration we can say that we will go for the hopper angle of 45 degree, and what for that you can find out from this equation that we are getting the friction less than 0.414, which probably satisfies all the combinations of the material of the part and the hopper wall. Okay. Now, for the reciprocating tube hopper feeder, the general features are the following, that optimum hopper load, that how much parts, how many parts you will be giving, you will be putting in this as a mass of parts. So, I will remind you that as we said, in this we have the parts, this is the level of parts. Okay. So, the parts are here, there are many of these parts. So, the idea is that it cannot be too much, it should be normally half the volume of the hopper. If it is more than that, in that case what happens is that the tube will be, pressure will be on the tube, and the tube has to move. So, that resistance to that movement, because the mass is very high or the parts are large in number, in that case the resistance is higher. So, therefore, optimally it is taken that half of the volume of the hopper. half the volume of the hopper. Delivery tube should just rise above the maximum level of parts in the hopper. What does it mean? The delivery tube, so that the parts can come inside the delivery tube, it is enough for the reciprocating tube to come just above that. I mean, it is not necessary to go beyond that, because it is absolutely redundant, and as we are moving that more, so that means we will spend more energy, will spend more power. Okay. Therefore, it has to just go beyond that level of the parts, just rise beyond the level of the parts. The inside silhouette of the delivery tube, this I have already told you, must be designed to accept only the correctly oriented part at one at a time. Now, I told you earlier when we were discussing the initial part of the lecture, that feeders, they have to feed the parts in the correct orientation. All right. So, therefore, there are some reorienting devices which are incorporated inside the bowl. Now, those things in details we will discuss at the later stage, but at this moment we are saying that if the inside silhouette of the reciprocating tube could be of the same type and the shape of the part and in that orientation which we desire, in that case through the reciprocating tube the parts with the right orientation can be taken. This is what exactly we are saying, that this is the inside of the reciprocating tube. Okay. So, inside of the reciprocating tube, the silhouette, that means the shape will be the same as the shape of the part. Suppose the part we want in this way. Okay. So, inside silhouette of this the reciprocating tube could be this way and not this way. Silhouette should not be like this. So, if the part is coming like that, it will not be accepted, because the inside silhouette of the reciprocating tube is made in the opposite in the different way. All right. Okay. So, apart from that, the linear velocity of the delivery tube should be less than or equal to 0.6 meter per second, meaning that if it is more than that, by inertia the parts may actually not go inside the reciprocating tube, and if it is not required to be made slow, because in that case it will not be, it will take more time. So, the production rate will decrease. Okay. So, that is why it should be less than or equal to 0.6 meter per second. So, it is around 0.6 meter per second, which is the delivery. Another thing probably I should tell you that this inside silhouette of the delivery tube must be designed to accept only correctly oriented part one at a time. Another advantage of this device I should tell, that if the inside silhouette is made exactly according to the shape, size and the accuracy of the part, in that case it can also give you as a kind of an inspection device, meaning that those parts which are quality wise which is right, only those parts will come. If the tolerance is not right, they will not be able to go inside the silhouette. So, that way many of the feeders actually made that way, so that this can be considered as an inspection device as well. Okay. Let us take a numerical example, okay, to see that how we can implement the theory that we have just now seen for the reciprocating tube hopper feeder. Suppose for a reciprocating tube hopper feeder with a static coefficient of friction between the parts and the hopper wall of 0.3945, determine the hopper angle so that the parts do not jam. See, this example is taken as a practical example when somebody is designing the reciprocating tube hopper feeder. Okay. So, as I said, I will remind you that for designing the reciprocating tube hopper feeder, the basic thing and the most important thing is the hopper angle, so that within the silhouette within the reciprocating tube and the hopper wall, the parts do not jam. So, here suppose the given is the coefficient of friction, it is 0.3945. Actually, we do not want anything else. For example, we know that we have this condition to satisfy for parts not to jam. Okay. So, here if we have the mu s given, we can find out the cos phi or the phi. That is what it is asked, that determine the hopper angle so that the parts do not jam. So, if you take for example is equal to 1 or less than 1, the parts are jamming or about to jam. Equal to 1, we said that this is the limiting condition. So, therefore, 1 upon cos phi plus mu s sin phi should be more than 1. This is the one which is which we have taken. For example, here if you see in this equation, if you see this, that this is the one that we have derived finally. Okay. And from here what we said is that these are the limiting conditions. So, therefore, in this example we are saying that 1 by cos phi plus mu s sin phi should be more than 1 for parts not to jam, and from here what we are getting is cos phi plus mu s sin phi is less than 1 if it is reversed, or mu s sin phi is equal to less than 1 minus cos phi. So, then we are expanding that and we are finding out that tan phi by 2 is more than mu s from here, okay. And finally, we are getting that phi is more than 2 tan inverse of mu s. So, therefore, phi is more than 43 degree because the mu given here is 0.3945. So, ultimately what you are getting is that phi has to be more than 43 degree, so that the parts do not jam. And here what is given only is the coefficient of friction between the parts and the hopper wall, which is 0.3945. Now, in the design problem, or when you are designing the reciprocating tube hopper feeder, you are using the part material of certain, let us say mild steel, and you are using a mild steel hopper wall. So, in the handbook you can find out between the mild steel and mild steel or any other combination of material what will be the mu s, okay. And from there using this equation, using this inequality, you can find out what should be the hopper angle. So, it is easy, you know the mu s, you can find out the value of the phi. Now, what does it mean that phi is more than 43? Anything 90 degree, 43, 90 is more than 43, can we use 90 degree? No, it is not like that, it is just cannot be less than 43, okay. And use that more than 43 judiciously according to the experience, that how much how many parts you will be taking. So, it suppose if it is 90 degree, you know that it will not work, okay. And so, accordingly from the experience you find out just more than 43, it should not be less than 43. That is the idea of this or the design criteria, okay. Next we will look into another hopper feeder. This is called the Centreboard hopper feeder, and from the name Centreboard you can find out from this diagram that is given in this picture. This is a pictorial view. So, here there is a bowl, okay, and inside the bowl we have the mass of the parts. These are also for small engineering parts, as in case of the reciprocating tube hopper feeder or the vibratory bowl feeder. Now, through the mass of the parts there is a blade which actually reciprocates, it goes up and comes down, all right, and it goes through the mass of the part. So, that means in here there is a cutout for this blade to reciprocate, and the mass of the part will be within the feeder. Here there is a chute or the delivery chute which is attached, which is fixed here. So, when the blade will come and align to the track to the delivery chute, then all the parts located on the track will be coming down the delivery chute and going to the assembly, going for the assembly to the machine, which are at the exit of this. So, the machines will accept the parts one by one which are coming from the sliding. So, therefore, what happens is here that this blade has to go up and dwell for some time, okay, so that all the parts could slide down the blade, that is one thing. Second thing is that here there is a pivot, okay. So, this pivot will be attached to this, the blade that you can see here, okay. The whole thing is actually moving, but the blade is here this much only, and the track which is given on the blade, on the track the parts will be nested. Okay. So, it is not along this, the blade is only this much, it is connected to this part, and this part is actually pivoted here. All right. Now, here there is one very important aspect that has to be taken care of. Now, the blade which is reciprocating, it is going up and coming down. If the acceleration is very high, okay, in that case at the top of the blade, the parts located on the track will be thrown out. All right. Second thing is that if the inclination is more, in that case the parts will be facilitated to come down. Okay. So, these are the two aspects, that one is that acceleration should not be very high, so that the parts are not thrown out of the track, and it should not be very low or very high. Of course, if the angle is more, if this track inclination angle is more, so in that case it will facilitate the parts to come down. All right. These are the two aspects, let us keep in mind. Now, this kind of centerboard hopper feeder, they are suitable for feeding cylindrical parts mostly. So, that means the silhouette of the track or the shape of the track is as per the cylindrical part, so that those parts in the right orientation can be nested. An optimum value of track inclination angle exists and theoretically shown to be function of only mu d and the RB by L, that we can see later on. Now, we are saying that optimum value of track inclination angle. If why it has to be optimum? If the track inclination angle is very high, in that case it will take more time for the reciprocation of the blade. So, more time is less production rate, because each time it is actually reciprocating in one cycle, it is feeding some parts to the machine, to the assembly machine. Okay. So, therefore, this track inclination angle has to be optimum. For example, for RB by L is equal to 2, what is RB? Is the swing radius from here to here, this is RB, this is the radius, and L is the mass of the part. Okay, sorry, small l is the length of the track. So, RB by L is equal to 2 and the dynamic coefficient of friction is equal to 0.4. This optimum angle around 36 degrees. So, these are given experimentally, there is a calibration curve which is made, and from the calibration curve you can find out that for the values of RB divided by L and the mu d, how much will be the optimum angle. There will be a calibration curve. Let us see this. Now, these are the two line diagrams given showing that how the forces are acting on the part when the part is at the highest position of the blade and when the part is coming down. Let us say when the part is here, forces acting on a part during the upward motion of the blade is like this. Here it will be mpg, that is the mass of the part, okay. And here is the normal force which is acting by the track. Here is the track and this is the part, and here there will be here what is shown is that this is the RB minus the L by 2, capital L is the length of the part. Okay. So, this is let us say at the middle of the part. So, therefore, it is RB total minus L by 2, this much. Okay. This is the angular track inclination, let us say, and this is the maximum track inclination theta m. In fact, here it is theta m, this is the maximum track inclination. So, when the parts are sliding down the track, here is the linear acceleration of the track, okay, mpg, n1 is the normal force, this is the free body diagram, and the friction force which will be coming here will be mpg cos theta m. Here what is happening is that we can actually resolve these forces. Okay. One force will be like this and one force will be along this, all right, and one force will be vertical to this, all right. So, mpg and the cos theta m will be here. This is multiplied by the mu d, which is the dynamic coefficient of friction. This will give you the friction force, and this is the maximum inclination of the track, all right. N1 is so we have three forces basically: friction force, mpg is the mass of the part, and the N1, which is the normal force. Okay. Now we can find out from the force balance equation here that what will be the condition for the acceleration. Okay. In the next class we will be discussing how the acceleration can be found out and how we can find out the maximum track inclination, so that the parts are not thrown out, okay, because of that acceleration, and so that the time taken for the reciprocation of the blade could be optimum. Thank you.